thank you very much to the organizers, again, for this. Actually, we should thank them, no? Also. Yeah, for inviting all of us. And thanks to all of you for still being here. So what I would like to talk about is something I'm a little bit dilettante on. So it's more of a test than, so this is work in progress, unfortunately. My collaborators have had babies, and it's become a little bit difficult to get them to do things. So anyway, so I've been doing this with Camille Bonvin, Nima, who's gone now, and Martin Kuntz. And the question I want to ask is really, if there were sort of vector mode in the velocity field, would we be able to actually see it? I mean, I'll review a little bit what I'm talking about. So, of course, I'll be talking about galaxy surveys, and what I'm interested in is the kind of the existence of some sort of vector mode at late redshifts. And in lambda CDM, essentially, this sort of thing. So vorticity only really comes from shell crossing in cold dark matter. So it's I'll show what it looks like, and it's kind of small and essentially kind of not really possible to see for all sorts of technical reasons. But we're at dark mod, so we can be kind of open-minded. So I will sort of consider make let's say comments about 4 possible scenarios where the signal from vectors might be enhanced, and in fact, we'll see how it works. So it'll be something like dark matter is not exactly cold. There's in principle possible that there's some slightly high vorticity. If there are some non-standard sources for density perturbations, I'll mention something like that. If acceleration is being caused by a vector, I'll put a big question mark on that, and I'll talk about something about having a preferred frame. But the main takeaway from this, hello, does this work now? Ah, it does. Okay, excellent. But the main takeaway, and maybe the only hard message, is that actually vorticity distorts the galaxy correlation function in a kind of funny way, and in principle, maybe there's something to be done by doing it, by measuring it properly. So, but let me go back to the standard story for those of you who sort of don't really think about things like this. So, in principle, so when we normally only consider scalars, because those are the perturbations which we expect to be large for the following reasons. So, okay, FRW metric with fluctuations, the potential sourced by matter, and then galaxies are accelerated by this potential, right? So they're moving on geodesics. They're massive observers, massive test particles, and they're moving on geodesics being accelerated by this potential. And then you say, well, if I observe these galaxies, so all I know about the universe really is from these test particles, but I make the assumption that there's the sort of weak equivalence principle, so that galaxies, dark matter, basically are accelerated by the same force, and they should have come from all the same initial conditions, so the velocities are the same. But I also know there's the continuity equation for dark matter, at linear order here, which tells me that the velocity and the density fluctuation are related. There's some corrections, but they're small, sort of reasonable scales. So what you can do is that you can actually, so this was Nick KAISER realized this a long time ago, that when you try to actually observe galaxies and put them on some sort of map and look at correlations of these galaxies, you don't really exactly see the density, the galaxies at the redshifts at which they are, because they have velocities. So really what you observe is some fluctuation in number density of galaxies, which is related to the real one, to the real physical one that's sort of added, in coordinate space, but it's corrected by the fact that this galaxy has some flow. You're only sensitive to the velocity which is radial, which is away from you, And this particular tensor structure will give us some sort of sensitivity to particular things. Okay, well, this you cannot predict really, but what you can predict is the correlation function. So if you just try to work it out, this is the standard result. So this is in configuration space, and essentially you find out that if you assume that the power spectrum is homogeneous isotropic, so depends only on the magnitude of k, then you get something like this for your for this 2-point correlation function, and depends only on the separation, the magnitude of the separation, and the of the two galaxies you're correlating, and the angle between the line of sight, which is this r here. So it's n is going to be some unit vector, and the separation direction. And depends in this particular way. You can decompose it, and there's a kind of monopole term, there's a quadrupole term. These are Lagrange, what's it called? Lagrange polynomials, Jesus, yeah. And the quadrupole here. The C's are essentially encoding the power spectrum, so it's a spherical, it's the power spectrum times some kind of spherical Bessel function integrated over all the k. So it's, and then these structures, and these beta is the ratio of the growth rate to the bias. So in principle, you can do what people have done this. These are kind of results from BOSS, the latest ones. You really kind of precisely measure the redshifts of the galaxies and so on and their positions. You get this. You can plot the correlation function in 2 dimensions, right? And you see that there's some that it's not exactly circular, right? So if it were really homogeneous isotropic, you would expect that the thing is that they have circles here. But you can see that there's a squashing effect, right? So there is some sort of there is a non-monopole term to this. You can plot the monopole and the quadrupole, and indeed various bins and so on at linear scales. You get something like that, and you can predict what this ratio should be. And this way you can measure beta, or in principle from that you can then get out something like a measurement of bias and measurement of of the growth rate times sigma. Okay, so this is all the standard story. I just want to say, of course, that once you get nonlinear, then you get lots of galaxies. So the error bars are very small, but in fact, because you have to find pairs, and you have to find pairs of pairs to get the quadrupole. So the higher the multiple, the harder it gets. Here you have large errors because there are not so many galaxy pairs that you can find, right? So the more galaxies you find in general, the better the results are, but this is what we can do right now. Okay, but everyone always considers that the flow is only scalar, right? So what I want to do is to reintroduce the vector. So normally what you say is that, well, there's just some velocity potential, and this velocity potential has a gradient, and that's where my velocities come from, and then the velocities always go toward over densities. So that's the standard part of this. This is the bit that's large, and this is the bit that this is what we study. But in principle, there's another part of the vector, which is there's another part of velocity, which is the real pure vector part, which is transverse, divergence-free. And from it, you can define the vorticity. Okay? So the question I want to ask is whether there's sort of any way, by looking at galaxies, that we can see this. I'll sort of try to say how this might arise in a bit, but first my question is really, will we be able to, do we see it at all, or not? So the way that what happens is that if you have vectors, then they induce this additional perturbation. So this is this is gauge fixed, if you want. So they induce an additional vector perturbation in your metric. The geodesic equation for the galaxies also gets some vector components. So the galaxies eventually follow this this particular vector in the metric, right? And the Einstein equations on the vector side look like this. And the reason why we never, so you can see that essentially the sigma is sourced by the vector perturbation of the matter, but if there isn't such a source, it just evolves to 0, so you don't expect to see anything. This is the reason why nobody looks like this, right? It's just, unless you have a source, there's no reason for it to be there. But if it were, who knows? I'm trying to be, what's the word I used? Open-minded. So on some level, you'd think that we're taking, so this distortion from the KAISER effect you know, it sort of involves derivatives, so you might think that in fact it's like a divergence, so in fact you wouldn't see anything because of this, because this guy's divergence free, but you're projecting on a particular direction in the sky. So so in the end, you're sensitive to a part of this structure. So let's keep this guy for the moment and try to work out really what that would look like. So, so for that to happen, so what I have in the back of my mind is this vector comes from just some, again, it's also some sort of fluctuating random field. And I'm going to assume it's also itself homogeneous and isotropic. But in principle, there may or may not be sort of particular directions that I like. But for the moment, let's consider the isotropic case. So really, the background's isotropic. There's no preferred direction anywhere. So you may think that there's something like this, which is a vector. But in reality, I can't really even think of how this would appear. But in case don't have a preferred background vector, this thing is 0, so you can just not completely forget about it. But what appears as a non-zero contribution is this sort of is cross-correlation of this guy, as autocorrelation of this guy. It appears with some particular tensor structure here. So there's the amplitude of the power spectrum, but there's a tensor structure. And if you want this thing to be these velocities to be transverse and isotropic, then this thing must be equal to this particular combination of k and delta. So this is fixed. You know, I've absorbed the amplitude into this, so this is the only thing that you're allowed to have. Okay. So given this, let me calculate, essentially do the standard calculation, but for this particular contribution. And what you find, so these are the standard contributions. And what you find is that you end up with something that looks like this. Okay, unsurprisingly, you end up with some additional contributions into each of the multiples. This is how I define this C omega, which is again something to do with the amplitude and the k dependence of this thing that I don't know for the moment. What I want to say about this. So in principle, people right now, we are sensitive to this, to the monopole and the quadrupole. This, as far as I'm aware, has not really been measured. The error bars, because you need 4 pairs of galaxies. We just don't have the statistics to get the error bars down on this, so this has not been seen yet. But going forward into sort of surveys such as this, in principle, they are planning to measure this object. So this, if you're thinking about this kind of scenario, gives you essentially a way to confirm that what you've measured is for B and F is in principle consistent with the hexadecapole. So, okay, this is a consistency measurement. If you add an extra degree of freedom, then in principle you may be able to, if you're willing not to have a consistency measurement, the inconsistency of this would give you some access to the amplitude of this, right? So if you can measure the 3 multiples, you would be able to say something about, if this exists, about the amplitude of these vector modes. Okay? If it's big enough. The question is, if it's big enough, what does that mean? So okay. So now to talk about if it's big enough, I need to actually say something about where this thing may come from. So one thing that is perfectly sensible to consider, and people do it, is look at, for the CMB, they look at cosmic strings, right? So cosmic strings are extended objects. They have directions, and as a result of that, they in fact induce vector modes, tensor modes too, actually, but the vector modes in the metric. So people have simulated, and so this is one of the simulations of some particular class of cosmic string models. They've run simulations. They've been running these simulations for many, many years, and sort of technology's there, but maybe the need isn't. But they simulated what the power spectrum of the vector modes would look like. So there's this funny property that is scaling. So essentially, provided that the solution to baryon cosmology sort of has a constant W, I mean just some power of A, you end up with a solution that just looks that depends really only on k tau, right? So on how much in the horizon you are. So this is some fitting formula that they have fit to what they've measured in the computer simulation. So these numbers look spuriously accurate. So the feature that is understood is this one. This is a result really of just conservation of energy momentum. This one, because, well, they're kind of correlated on horizon size because they haven't yet interacted, so they're kind of correlated. Then they begin to interact, and they begin to get less correlated, and then nobody, well, this paper says that they don't really know how to explain this very much. But you get some shape. The point is that from my perspective, all I care about, I want an amplitude and I want a shape. So the CMB constraint today is of this order on this parameter, which is essentially the energy scale of these, to use the energy scale of these of the theories of describing these cosmic strings. So you can see, you know, and we try to play around with this to see what Galaxy servers might do, and you get constraints which are completely uncompetitive, right? But the theme is that if you have the amplitude being peaked at the horizon, then essentially you have no hope because no galaxies on those scales, right? So, well, okay, but but this is just in principle, might have worked. So let's talk about dark matter. There are two things that sort of might happen. So this vorticity gets generated it gets generated at higher order in perturbation theory. So I said the linear order, there's no source. But higher order, you get contributions from the square of the metric, but those are always tiny and irrelevant. We also got contributions really from the energy momentum tensor of the dark matter because you get shell crossing. So what happens? The fluid eventually various streams of the dark matter cross each other, and you have to re-average the fluid. And when you re-average the fluid, you find out that in fact you have a new velocity field. That this new velocity field is vortical. It has some contribution of vorticity. So there's a paper by Scocimaro and Pueblas from about 10 years ago where they actually, in n-body simulations of CDM, they tried to measure what this vorticity would be. This is hard to do because you're not really, it's hard to, you're sampling the space very poorly with your particles, and then you have to somehow figure out what the velocities are, and that's a very hard thing to do. But they seem to be satisfied that this is what they've measured for CDM. So you get something which, is peaked at k of 1 and has some particular K structure that from the diagram looks something like this. From their paper, it says something else. But from this plot, it looks like this, and the paper justification says k squared there. So, so we kind of try to essentially just like I said, all I really care about on this level is the shape and the amplitude, right? So it sort of flattens out here, it falls off here, it grows here. So on this, so what confuses us a bit is the scale. On this particular scale, what you find is that for something like DAISY, so this is now we're actually putting realistic sort of surveys in, you're in principle sensitive to this kind of numbers. It's just a Fisher forecast. But of course the problem comes, this comes from nonlinear scales. So coming back to this sort of, how I work this out, the two sort of modes are not really going to mix, right? The vorticity of the velocity field is the vorticity of the velocity field. So the fact that there are some nonlinearities doesn't matter. I can really separate the two and measure the vorticity. The issue is that what I don't know when you get to nonlinear scales is really what the bias is doing and really what f is doing, because the growth rate is no longer the linear growth rate. It's a more complex issue, and so if you understood that, so in lambda CDM, if you understood that very well, in principle you'd be able to at least, you should really add this component. So if you ever are in a situation where you understand the power spectrum well enough to be quite certain of the, really what the growth rate is and so on at small scales in lambda CDM.
Quick question.
Yeah.
In this case, even at this scale, the notion of velocity is not very clear, because we have multi-streams.
So they average, so they really.
Yeah, but this is what you will measure.
Yeah, well, so what you're measuring is the metric, right? Really. So it's your galaxies, which are moving on geodesics, so which are essentially the sigma. So that's the metric, and the metric is in some sense sensitive to the average energy momentum tensor, right? So it doesn't know about the tiny, it doesn't know about the individual particles, it knows about the gross behavior of the averaged fluid, right? So the average fluid velocity has some, on average, has some vorticity, then it should know.
Yeah, it doesn't look to be obvious that this is what RSD will measure.
So RSD measures the peculiar velocity of galaxies, right?
Exactly, and they are not, they can have two galaxies kind of close to each other with very different velocities.
Sure, but you correlate. And you're looking at the correlation of that on some particular scale, which takes out the small scale stuff in direction, and you're just looking at some scale. Problem is, of course, at these scales, it kind of gets complicated. Yeah. No. So I'm not sitting here saying that. What I'm saying here is that in principle, if you ever get the sensitivity to actually hope that you understand the scalar power spectrum well enough to be able to say something at those scales, then you should also begin to worry about this, because that's a contribution. But it's not. I mean, it's more of a realistic survey. If you understood the systematics well enough, would be sensitive to something like this. So I would subset from the outset that it's completely hopeless to talk about vorticity. I'm sure most of you think that, right? So but here I'm getting a sort of amplitude which is sort of not 20 orders of magnitude below what I'd expect. Right? That's all I want to say. But of course, the point is that you're sensitive at the scales where lots of galaxies, right? So there are lots of galaxies here, so you're very sensitive here. So you have a peak here, then you're good. You have a peak at at the horizon, then you don't see anything essentially. That's the. Now, what I want to say is that in principle, dark matter is, so this is a different calculation. So this was really a simulation of CDM. This is a paper by Rudure and students. They did perturbation theory, but they added dispersion into the original phase space distribution of the dark matter. So it's somehow a little bit warm. And it's some perturbation theory calculation. So what happens is that they generate vorticity because of this. The scale has changed, as you'll see. But the errors I told you before would be sensitive to something like this. This is dispersion today, if you want, according to the model. Which, if you look at this plot, which is sort of somewhere around here, that's the sensitivity that we have. Okay, dark matter, CDM is sigma 0 10 to the minus 14. Okay, so this particular contribution is irrelevant for CDM. However, if you're looking at something that's warm, but also I think kind of helpful, but warm, but quite warm, you in principle might be able to begin to see some vortical modes. How much time do I have? 5 minutes. Okay, so then, but this is like normal stuff, right? So then vectors from acceleration, I just want to say I have no idea. So the idea is that if you really have a vector that's driving acceleration, in principle you have vector modes. Would they actually be also enhanced in some? They'll be there. Will they be enhanced gravitationally if it couples to gravity in some way? I don't know. But if such a model exists, it's sort of in principle visible in this way. And I just want to finish quickly on this, which is that what if you have anisotropy? So this is actually how I kind of started thinking about this, is that can we really think of this omega as being some sort of remaining signature of the fact we're expanding a little bit around the wrong metric? So we have constraints on isotropy, of course, from the CMB, but if you think about it, it's about the CMB is very isotropic, and you integrate from there to today, you're kind of sensitive to the late universe, but but not so much. It's mainly really about the isotropy of the original structure. So what I would like to understand is really, can we sort of test isotropy like right here locally? And this gives you a way. So it's not sensitive to the actual change in the distances, the relative, because of this derivative, but it's if there are vectors which are driving this anisotropy, then in principle you might. So you have again. So coming back to this calculation originally, you have this guy. Again, I can't think of why this would not be zero, even if you have a vector, because you have to correlate galaxies with this velocity. But in any case, in flat sky, it's not there. But then this structure gets a whole other set of contributions, which are it's a trace-free symmetric matrix that is zero when you trace it with K. So when this was isotropic, anisotropy adds you this guy. So this is a symmetric matrix with zero trace. So you can expand it in some basis. So in principle, there are three sort of eigenvectors of this object. And with some three eigenvalues, which tell you about the relative amplitudes of the anisotropic part of the contribution to the isotropic one. So let me forget about the fact there may be three. Let me keep one. And so I mean, all I want to say here, so this is something that we're doing right now, and sort of it's not finished in any sense. But so the question is, how would you know that? How would you see this? So if you try to work out the correlation function when you have such an object, then you get clearly a whole new set of contributions, because there's now two vectors. There's n, but there's now this vector omega 1, right? And in principle, you get dot products of both of them. And OK, this is not the whole result. The whole result is horrible, but it's actually rigid. So it only depends on the amplitude and the structure and the shape of the power spectrum, and all the other you know, it's essentially a bunch of Wigner 6J functions, which if you expand into something more pedestrian than I understand, they're just products of Legendre polynomials, but mixing the dot product with n of the separation and with this omega. And now the interesting thing is that if you do the standard analysis, which is that you would like to plot the correlation function as a function of omega, you average over all these guys, and they all go away. So by doing the standard thing of the analysis of the power spectrum, of the correlation function, you erase completely this signal. Now, how to actually extract it is a sort of is a thing we're thinking about right now. But in principle, it's possible to take away the isotropic part and try to somehow constrain the amplitude of this anisotropy, which is the anisotropy at late times. So really, if you think about it, it's the fact that the galaxies themselves locally have an anisotropic distribution around them. It's really not to do with us, it's to do with them. So that's it. So I finish here, and so what I wanted to say is that we want to find new observables that will test the consistency of lambda CDM, because it's, you know, we're desperate, right? So vectors give some contribution, even if you have a sort of conservative isotropic idea. But if you have a preferred frame, and of course the question is whether this sort of, you know, their preferred directions like this, where they would have known about this from solar system tests, which is another, that may well be a much more powerful test still, whether they would have known, you know, whether we could see this. But I don't have a model actually to really say what we're looking for. So actually, if anyone has a model that they would like to suggest to me, that'd be very great. Thank you very much.
Thanks a lot. Do you have questions?
Oh, everyone hates me. Okay.
A comment.
Uh-huh.
It's true that it's interesting to test the isotropy at low redshift, but the constraints on this from the CMB on that type of anisotropy are at level of 10 to the minus 11. So the question is, how can it be competitive?
Yeah, so the question there is to what extent anisotropy at redshift, so that say 1, some small anisotropy at redshift 1 would have affected the isotropy of the CMB, right? Compared to something like this. I mean, so that I don't know. So this is a thing, this is, like I said, it's a work in progress. So this is a calculation I must do. So yeah, you're right to be skeptical, maybe, you know.
Sorry.
But it gives you a cross-check, you know, on some level.
So again, in connection to the CMB, so I mean, of course, there have been lots of techniques developed for CMB, I mean, to look for like anisotropies and all that. And I mean, here you're talking about 2-point correlation functions with basically power spectrum of correlation function. But you know, when you have an isotropy, you have off-diagonal, you know, terms in the covariance matrix, right? So you cannot just use the power spectrum, not the diagonal part. So I mean, you have to take into account the full covariance matrix. I don't know, I mean, how you're going to do that, but that's what you mean. So basically,
well,
by a new manner, you mean like really including the full information, or how?
No. So wait a second. So so this may depend on really how you define this. So what I've defined is that there's a power spectrum of fluctuations of this extra degree of freedom, of some degree of freedom, right? Which is isotropic and homogeneous, but the background, but it has a preferred direction. So there's a background sort of omega. This omega tensor is a background tensor, and there is a homogeneous isotropic set of fluctuations on top of that. I'm sort of thinking it's a linear kind of thing. Then that's all you get. So I just correlate density at 2 points, I work it out. That is all you get. I mean, what matrix would I put in here? It's like there's just delta 1 and delta of R2, and I cross-correlate the two of them. And this is no, it's a horrible answer, but it's an answer like that.
But the map, I mean, well, I mean, the data that you're using, really. I mean, I mean, this anisotropic is in the data, right? So you basically that's there. So if you, for example, look at sky or whatever, you have all these things like a random field. So that random field is actually not isotropic, right?
Ah, sorry. So you mean, yeah. So I'm predicting that in case of anisotropy of the kite I'm saying, the correlation function will have a structure which will involve two vectors, n. So if you want this mu that you normally use, and another one, right? Okay. So in principle, given so now I need the three-dimensional structure I need a three-dimensional map. But if I knew what the right estimator to use is, I would be able to extract the amplitude of the anisotropic part of this and a direction of this vector. Well, I need a 3D map because there's an additional vector. So maybe that's what you.
So you cannot work with it just spherical kind of like whatever like.
You cannot. No, I mean you cannot work with 2D power spectrum. Yeah. You have to actually understand really where the galaxies are in three-dimensional space because you have two vectors.
Thank you. One last question.
Just a quick question. What about the preferred frame? You promised us that you were going to talk about the preferred frame.
It's that. So I'm saying that there is for whatever reason, there is something which is sourcing the metric, which in fact knows about some direction in space, and it's encoded in this W tensor here. Yeah, that's exactly what gives you this anisotropic contribution to the correlation function.
Okay, thanks a lot.